So what I have here is a video by Bob Eisenstein about relativity, which is giving to some students, and I want to complain that it's nonsense. A great deal of nonsense is being taught here, and there's so much of it that I'm not going to be able to go into all of it. I'm going to just get to some of the essential nonsense and point it out to you. Let's start it up.
Squared. Because Jerry Garvey, last year or so, gave a very nice talk on E equals mc squared, so I'm not going to repeat that. So anyway, it's a great pleasure to see all of you here, and I didn't know there were this many relativists in Santa Fe, but I'm glad about it. So we're going to talk about Albert. Now, the things we're going to talk about tonight were things that he did in the early part of the 20th century. He finished his work on special relativity in 1905, and he finished his work on general relativity in 1915. And 85 years went by between then and the end of the 20th century, and still, in the Millennium edition of Time magazine, their person of the century, it's Albert Einstein. So I find that a pretty remarkable comment on how much his thoughts have meant to all of us, and how he changed so profoundly everything we understand about space and time. So the other thing that's really magical about him is he had the most penetrating insight you could imagine, and he did it from the simplest kinds of assumptions that you could imagine. In fact, you'll see many of the assumptions tonight, and they're things that we all see every day and think about every day a little bit, but in Albert's head, they become something truly extraordinary.
So he's trying to lull you into a false sense of security. You're going to come from some simple concepts, and it's supposed to be then twisted around and made into something complicated. And it's a long process of lulling you into something which seems to make sense until it becomes nonsense.
That's the first thing. The second thing is that Albert made advances in realms that have no direct relevance to us in everyday life. His advances were for objects that are moving at high speed, and for objects that are at great distances in the universe, and the cosmic structure of the universe. And these are things that are, let's just put it directly, they're pretty remote from everyday experience. So what are we going to talk about tonight? First is we're going to ask questions like, are there such things as absolute space and absolute time? We're going to talk about some important properties of light. We're going to talk about the notion of space-time. We're going to talk about what world lines are. These are the general topics that fit into special relativity. Then we're going to take a leap, as Albert did in 1905, and extend special relativity to try to include gravity, which he did not include at first. And then we're going to talk a little bit about how it determines the nature of the cosmos that we see today. And then I also want to show you one example of how it's actually useful in everyday life in a way that maybe you know about and maybe you don't. And that's general relativity. Okay, so let's start by talking about another great physicist, Isaac Newton, who lived in the 17th century. And at about age 25 or 26, he conceived of his theory of gravity, which we won't talk about tonight, but which if you've studied high school physics or college physics, you already know something about. The main reason I want to talk about him is because in his world, there was actually such a thing as absolute space. All of the events in everyday life took place on a backdrop that's rigid, immutable, fixed, never changing. In addition, time was considered to be absolute, so that you, observing an event, could establish without any doubt what time it took place and where it was. And it would be the same for everybody in the universe. They'd all look at that same event and make the same statements about where and when. So absolute space and absolute time. Okay, well, now I mentioned that things took place instantaneously, or appeared to take place instantaneously. And the reason for that, it turns out, is because people could not measure at that time what the speed of light was. The speed of light is extremely fast. It's not observable in any real sense on a day-to-day basis. It travels at 300 million meters per second. That's once around the world, 7 times around the world in 1 second, so it's really moving. Just to give you an idea, light goes very fast, but it doesn't go infinitely fast. So it takes 8 minutes for light to reach the Earth from the sun. It takes 8 hours for light to cross our solar system, and it takes 100,000 years for light to cross the Milky Way. So that's just to give you some idea. Light's very fast. We rarely know that it's, there. The old Satchel Paige joke about turning off the light and getting into bed before it went out. That's not possible. So one last thing is I want to convert this enormous number to a different number, which I hope will be a little bit easier to understand. This speed, 300 million meters per second, is the same as 1 foot every nanosecond. So if I stand here in front of this gentleman, I'm about 4 feet away. It takes 4 nanoseconds. Each nanosecond is 10 to the minus 9 seconds, a billionth of a second. It takes 4 nanoseconds for the light to reach me from him. That means that I'm seeing him the way he was 4 nanoseconds ago. And similarly, when I look at the sun, I'm seeing the way it was 8 minutes ago. And if I look across the solar system, I see it the way it was 8 hours ago. We'll come back to this later. The basic notion is that distance is look-back time. When you use light as a reference, you're seeing things as they were when the light was emitted. Okay. All right, now, here's one of the ideas that in the brain of Einstein became something pretty profound. So we're going to talk a little about relative motion. And the question there is, who's moving? So, Maureen, would you... Oh, it didn't work. Just a minute. Try pushing one of the arrows. Well, I guess it needs a mouse button. I don't have a mouse on there right now, so I guess that's why.
So he's still into a long process of trying to lull you into a false sense of security about how it makes sense. Unfortunately, his little demonstration here didn't seem to work, so he has to talk through it. Here we go.
Try it again. Well, I don't know. It isn't working. But what it is a film taken by a man in one train of a train passing by. And the point of the film is that you can't tell who's moving. You've all had that experience. You sit in you can't tell whether it's you or whether it's the other train. And that's just the way it is. So the point that Albert tried to make and did make was that both viewpoints are equally valid. It's not a question of one being right and one being wrong. They're both correct. So we're going to talk about this time and time again, about how you have two people observing the same thing, and they see different things, but they're both equally correct. Okay, so let's go on. I'm sorry that clip didn't work. All right, now let's talk a little bit about moving at a constant speed. Now, you've all had the experience of sitting in your car when it's not moving. You can see that it's not moving because you can look outside and you're not moving. You've also had the experience of moving along at a constant speed and not feeling anything. And the extension of that is that if you were in a dark room and actually moving like that, you couldn't tell. So there's no experiment that you can do inside a car like this one, a darkened car when you can't see out. There's no experiment that you can do that will determine whether or not you are moving at uniform speed. Now, if you accelerate, or if you slow down, or if you turn right or turn left, that you can feel because the car has to force your body to change direction or change speed or something, and that you can feel. But if you're moving at constant speed, you cannot tell whether you're in motion or not. So this is an important principle of relativity. So we've now done two things. One is you can't determine about relative motion, and now we're determining that you cannot tell whether or not you are in motion. So in a closed space, you can't tell if you're moving or not. Okay, so when you have a constantly moving frame like that, or car, let's say, we call that in the phys biz, we call that an inertial reference frame. So I'm going to refer to it that way from now on. So what have we learned so far? All inertial reference frames are equivalent. There's no experiment you can do to tell if you were in motion. We haven't learned it, but you won't be surprised to learn, since you can't tell what's going on, that the laws of physics have to be the same in each inertial frame, and they are. And so the conclusion that Albert came to about this, and actually people before him too, Galileo had some of these ideas a long time ago. Therefore, none of them is privileged or absolute. Everything is relative. Each person sees the world from their own equally valid reference point. All right, now...
Right, I want to complain about that a little bit. Get back to it. He's talking in the context of constant velocity when there's no acceleration. So the motion he's talking about is constant velocity and no acceleration. For that, you can't tell if you're in motion if you're going at constant velocity. And that's if you're in your darkened box and you're not able to see outside of that box. And then we get down to something like this. Therefore, none of them is privileged or absolute. Everything is relative. Each person sees the world from their own equally valid reference point. Now, that must be in the context of constant velocity, but he's leaving it unclear as to that whether that means also in the context of when you've got acceleration. So people can look at that, and some people can think, oh, that only refers to when it's constant velocity motion, and other people can look at that and say that also applies when it's acceleration. So he's not making it clear on this issue. What does that apply to? What type of motion? And that's ambiguity. And all these people who believe in relativity, especially those who teach relativity, most of them start making ambiguous statements like this. They're not making it clear. They're not clarifying things. And so that's my gripe with that. There are people who get the wrong interpretation of something said like that.
Leo had some of these ideas a long time ago. Therefore, none of them is privileged or absolute. Everything is relative. Each person sees the world from their own equally valid reference point. All right, now let's talk a little about simultaneity. What's that all about? Well, let's do a little thought experiment, as Albert would have done. Let's suppose you have a young guy and a young girl standing exactly 10 meters apart from the center from this location, and a lightning bolt strikes. Now, light comes from the lightning bolt to each of them. It takes a little bit of time to get to each of them, but they both see it at the same time, and they both record the same time for that event. So observers on the ground see the bolt at the same time. Now, what about observers on a moving train? Let's suppose the boy and the girl are on a train that's moving to the right, and at just the right minute, the lightning bolt comes down and hits at the center of the train. What do these two people see? Well, since she's moving away and he's moving toward, he sees the bolt before she does. So they don't agree that this is a simultaneous event, whereas these two people do. And so this is another part of relativity, which is that whether things are simultaneous, what you observe depends on your state of motion. Okay? All right, let's continue a little bit. Okay, now here is, first of all, a painting done by my good friend Orlando Leibovitz, which we're going to talk a little bit about now. So it turns out that Albert is very famous for, even as a young person, doing what he called in German Gedankenexperiments, thought experiments. And as a young person, the story is that he wanted to know what it would be like to ride along on a light beam, and whether you could ever catch up to a light beam. So this is Orlando's sketch or drawing, painting of Albert riding a light beam, and he actually has an accurate representation of what a light beam looks like from an electromagnetic point of view. So there's Albert. Another experiment he did was to ask himself, well, what if I were moving along and trying to look at my image in a mirror? If I could catch up to the speed of light, then I would no longer be able to see my reflection in the mirror, because I would be going faster than the light coming off my face. For reasons only Albert knew, for him this was a completely unacceptable answer. So he just refused to accept that. And so he made two propositions which were stunning, and to my mind they're really the heart and soul of special relativity. So what are they? First of all, nothing can move faster than the speed of light in a vacuum. Everything. That is universal speed limit. Secondly, believe it or not, the speed of light is the same for all observers, even if they are moving relative to one another.
Right. Now my gripe with this is, this presumably altogether is the postulate about the constancy of light speed, which is Einstein's second postulate in his paper on special relativity in 1905. Now I've seen this stated in lots of different ways, and I don't really get the impression that the speed of light is a limiting speed from it. By saying that the speed of light is a constant, I wouldn't say you can necessarily say that as well with it. So I dispute the ambiguity of the light speed postulate. It is not clearly stated. It's stated in lots of different ways, and I don't think they're all equivalent to each other. So it's ambiguous again. But carrying on.
Now, how can that be? So we're going to say a little bit about that. So let's talk a little about how Galileo would have seen relative motion. So here is a girl riding on a train and walking on the train at a speed of 2 kilometers per hour relative to the train. And the train is moving at 5 kilometers per hour. So what does the boy on the ground see? Well, relative to the train, the girl is moving at 2 kilometers per hour. Relative to the ground, where the boy is, she's moving at 7 kilometers per hour. What could be easier? You just add these two speeds together.
Okay, I want to clarify this. So this is my little diagram of it. You've got this box representing the train, and taking a point on the train from a point which the person outside is saying is stationary. From that point to that point, it's 5 kilometers per hour. And if that point is the girl that's walking forward at 2 kilometers per hour, then those two things add together and you have 7 kilometers per hour. So the person outside, the boy outside, is saying relative to this point, the girl is moving at 7 kilometers per hour, and the train is moving at 5 kilometers per hour. So you're taking a point on the train which is moving relative to this point, and I want that clarified. So you've got 5 kilometers per hour from that point to that point, and from there to there it's 2 kilometers per hour, and the total thing is 7 kilometers per hour. So I want you to remember this diagram. I'm going to come back to it as we continue.
Together, and that's it. That's what Galileo said, and that's what Newton said, and that's what we believed up until Albert came along. But here's the deal according to Albert. Let's suppose you have a rocket ship, and let's suppose it's going at 1/2 the speed of light, and it emits a light beam. According to Albert, that light beam moves at speed c, and furthermore, the rocket ship can never catch it. It's not as though this light beam goes at only half the speed of light compared to the rocket ship. It goes at the speed of light, no matter how fast this thing is going. Now, what about the girl on the ground? What does she see? Well, she sees a light beam going at speed c, and she does not see a light beam going at 1.5 times c, which what Galileo would have said. He would have said, well, this thing is going at half of c. It throws something out going speed c, so therefore on the ground it would be 1.5 c. But it isn't.
So they're talking nonsense there. So I'll clarify it. From Galileo, you've got from that point, which is stationary for the person outside, to the spaceship, it's supposed to be going at 0.5 c, and the light is leaving from that point at speed c. So the speed from that point is, for the light, is 1.5 c. That's Galileo. But instead of that, he's trying to get to say, from that point it's c, and from that point it's c, even though that point is moving with respect to that point, which is nonsense. That only makes sense if that point is really stationary with respect to that point. If it's a moving point, it doesn't make sense. So for the rocket, spaceship, we've got, it should be this, that point stationary to the person outside, the rocket going at 0.5 c to that point in the rocket, the light leaving that point at c, you should be getting from that point the light as 1.5 c. Compare now to the train case. So for the train case, from that point it's 5 kilometers per hour to a point on the train, and for that point, that as the girl's walking along at 2 kilometers per hour, we get the total speed for the girl, for the person outside, as being from that point as 7 kilometers per hour. So for the spaceship case, it should be exactly the same. You should be able to get from that point 0.5 c, corresponding being similar to this 5 kilometers per hour, and at 2 kilometers per hour case here being similar to that c there. Those two things add together. Those two things should add together. But instead of that, instead of it being sensible like that, they're trying to talk nonsense that the speed from that point is c and the speed from that point is c. But even though that point is moving is 0.5 c, which is nonsense. The person here would not be saying that c and that c. He would be saying that, he'd be saying that from that point it's 0.5 C, from that point it's C, and from that point it's 1.5 C, and that would be what he would sensibly say instead of the nonsense. So he's just given nonsense. So back to him again.
And that is a remarkable thing. And as I've said before, if you ask me what is the heart and soul of relativity, it's these two postulates: that the speed of light is a universal constant and an absolute, and secondly, that it is the same to all observers. Now, how can that be? Well, it must be that these two people, they're in relative motion with respect to each other, remember. One on a rocket ship and one on the ground. They must be seeing space and time differently. So what difference does that make? Well, if they both have to get the same number for speed of light, c, it has to be a constant. One of them might be measuring a large distance divided by a large time. The other might be measuring a small distance divided by a small time. But they have to get the same answer for c. So the key is each observer is seeing space and time differently. If that's the case, then space and time must be linked together in some way, and they're not independent of each other. They depend on the state of motion. So what you see depends on how you are moving. We call this linkage space-time. That's the word we give it. The linkage between space and time. We'll come back to that.
So there you go, that's absolute nonsense. That is his linkage to space-time. So instead of this sensible arrangement of from that point to that moving point it's 0.5 C, and from that point the light is moving at C, and so from that point light is moving at 1.5 C, he's trying to tell you the light is moving from there as C and moving from there as C, which is absolute nonsense. And that's how they build their relativity up. They just talk nonsense like that. It has nothing to do with how physics is dealt with. Dealing with physics, it was back to that case of the girl on the train. From that point, which is according to the person outside is taken to be stationary, to a point on the train, that's 5 kilometers per hour, and if the girl's moving from there at 2 kilometers per hour, then from that point it's 7 kilometers per hour. You cannot suddenly try to stop doing that when you go to the spaceship. They're just trying to confuse that point and that point, which is nonsense. You cannot do that. That point the outside observer is going to take as stationary, and the outside observer is taking that point as moving. You can't suddenly say, oh, it's C from there and it's C from there. It's not. That point is stationary, that point is moving, so it would be different. And so building from that nonsense, they just carry on. So what they could be doing is messing up light beams. Relative to this point, the light is going at speed c, and this point here, this point is moving at speed 0.5 c. So relative to this point, the light is going at speed 1.5 c. Now they might be messing up and muddling it up with this case we've got two different light beams, light beam 1 and light beam 2. Light is being emitted from here at speed c, and light is being emitted from here at speed c, and that's two different light beams, light beam 1 and a light beam 2. Whereas here you're just considering one light beam as being emitted from here, and then you're considering it relative to this point here. So that's what they might be doing. They might be muddling up with this. And another issue they bring up is about relativistic velocity addition, but Bob Eisenstein is not actually talking anything about that. So based on what he's saying, he's trying to talk nonsense here about this light moving at speed c from here, and then trying to make a mess of it by trying to say it's moving from points from speed c from here as well, when actually it's not. It's relative to that. If light's moving at speed c from here, and if that point is moving at speed 0.5 c, then relative to that point the light is moving is 1.5 c. So that's how they mess some things up.